in this section, I'm going to talk about some of the fundamentals of PuMA. And so I assume that you've already watched the first couple of videos, the first one on the installation and the second one on the setup of a Python project inside PyCharm. So I'm gonna just start over again from the Python project that we've created. Something that I wanted to let you notice is that every time that I run a pumapy function, a log is created inside the logs file, the logs folder that also gets generated. So as you can see, I've already run this functions several times. So the first quick example is gonna be about just creating the most fundamental basically class inside pumapy, which is what is called a workspace, which is responsible for holding your domain and all the information about it, basically. So in this case, I'm generating a small domain, just 10 cubed, and every single voxels inside this domain is gonna have a number of an ID of 1, and then I'm just gonna volume render it. So let me and by the way, right now I'm basically running the script inside the Python console, which is an option inside the edit configuration inside PyCharm. So if I now show the window pop-up, here is our 10 by 10 by 10 domain. Everything has the same value of 1 in this case. So I'm just gonna close this example and jump into the next one, which is more interesting. The second one is about importing a real domain of Fiberform. Fiberform is a real material that we study for heat shield applications. And so this is one of the examples that gets directly shipped with PuMA. It's inside PuMA Python, pumapy data. These are all the files that get shipped with the software, and so you can load them by simply using the path to example file that is automatically gives back the path to that file that you specify, and then that's imported inside using the import 3D tiff. So if I run this function, it's gonna store the domain inside this workspace WS Fiberform, and it's gonna first thing is gonna just render the whole volume of the 3D tiff. And here it is, like every single voxel is now, as you can see, a grayscale intensity value given from microCT. And so one of the first things that we would like to do is basically separate out the fibers from the air phase or void. So the way that we do that is basically by thresholding it. In this case, it's a 8-bit TIFF image, and so it has values that go from 0 to 255. And so in this case, we give everything that is from 100 to 255. We say that that's a solid, and so I'm just gonna basically threshold it and volume render just that phase. And as you can see here, I'm just coloring also the edges just to show you that this Fiberform domain is made of like many little cubes or voxels. And so another thing that we can do another rendering function is the contour. So in this case, we are rendering an isosurface that is triangulated throughout the specific cutoff range that you can input inside the function. So let me close that. And so next thing that is gonna basically do, forget about this slicer for a second. The thing that is basically has already run is the binarization of this domain. So we're gonna give everything that is between 100 to 255 an ID of 1, and everything else is given a value of 0. So it's not necessary to do this, but I wanted to show how to basically segment out how you would actually change the values in your workspace matrix using this binarize range function. Then another simple geometric property we can compute is just the porosity. So you can just call this function dot porosity on your workspace, and here it is like printed out. In this case we have a workspace that is 80% porous. Then next section that I'm showing here is basically how to rotate, how you could go about and basically rotate your domain, in this case by 45 degrees around the z-axis. And so here is basically how it's showing it side by side with the original Fiberform sample and how it looks rotated. Something else that you need to be careful with is the boundary modes. So we want to basically interpolate the functions using the reflective boundary conditions on the sides. So moving on, the next thing that it's gonna output is basically just filtering. So we, in PuMA, this is just an example, but in PuMA, a reference that you should always keep in mind is the documentation. So you can basically access how to use every single function, and we have implemented several different filters in PuMA, including morphological filters or image filters. So for example, for morphological we have dilate, erode, or closing, etc. For more image filters, like image processing filters, we have Gaussian, mean, and median currently implemented. In this case, I'm giving an example for the Euclidean distance. So for this specific like Fiberform domain that we've already binarized, we have given like an ID of 1 to the solid and 0 to the air phase. So what the Euclidean distance is going to compute is basically the distance inside the solid to the closest air voxel. So if I show this, here it is, basically the contour map for these ones. And if you can notice in depth in the material inside the solid, we have a lighter color. And that is because the closest air voxel is further apart. So that's a pretty commonly used filter. So now the next thing that I'm gonna show you, let me comment this out, is a generation of a random fiber domain. So in this case, this is a pretty powerful function which takes quite a few inputs. And so again, what I would recommend is going inside the generation and looking for fibers, and there it is. So for every single input, you can basically have a reference of what it's expecting. So the first one is the size of the domain. The second one is the radius of the fibers, and then the porosity of the domain. And then this phi and theta are important because they control the orientation of the fibers. And finally, whether these fibers can intersect, and if every single, the segmented one is whether every single fiber is given a unique ID directly, or non-segmented as if it was microCT. So let me uncomment this and comment this one, and I'll run this one. So what's gonna basically generate it is a random fiber domain, which you can see right here. So I could have probably given it a smaller radius, but anyway, this is just to show you. And this is basically running the render volume on that domain, and the cutoff that I'm currently giving is from 1 to the maximum ID of these fibers that have been generated, and 0 is for the gas phase or void. So the second thing that it's gonna output is basically is gonna render is the orientation. Since we're generating these domains, you can basically, it's gonna output directly the orientation of these fibers that are generated. So it's just gonna take a second. There it goes. So here is the vector field, where basically at every voxel we have a specific vector pointing in the direction of the fiber orientation. So now if I close this window, the last thing that it's gonna run is basically it's gonna export this domain and both the orientation and the matrix inside a VTI file. A VTI is a pretty commonly used file format, and it allows you to not only store like an image, like a TIFF could be, but also a vector field in this case. So in this case, I've specified to output it to my downloads, and this one can be imported directly inside other softwares such as ParaView, for example, which are able to read this VTI format. As you can see, if I import it in here, we have both the data and the orientation. In this case, I can show it very quickly, our fibers. Okay, so the last example that I want to show, and let me close ParaView, is a last couple examples. One is for another type of artificial domain. In this case, I forgot to change the name. Is for a random sphere domain. So basically, we are scattering spheres all over the domain and the spheres are generated with I think it's the diameter of 20 voxels, and it's giving it a porosity of 80% again, and then finally it's letting the spheres intersect, and it's segmenting them automatically so that every sphere has a single unique ID. So by rendering this domain, and this is much bigger, it's 400 cubed, as you can see the spheres have been generated. Something that I'm gonna show later is that this type of spherical domains can be inverted so that you can basically have a spherical porosity instead. So if I close this, at the very last example I want to show is one of the latest materials that we are able to generate. They're called TPMS, or triply periodic minimal surface. And so we have three different equations that we can run, and here's like in the input you can give, and these two are two parameters of those equations. So these materials are of interest for combustion applications. So this is basically one of the types of materials that we can use, the first equation. The second one is going to be rendered in a second. Here is the second type of material. And then the third one, TPMS material, is going to be this one. So a bit less porous. So this concludes the section about the image manipulation, data import and generation, and visualization.